Welcome everybody on Zoom, welcome everybody in the lecture hall, everybody from the future. Today we are going to cover Spark, finish covering Spark, and then we'll move over to document stores. The clicker here doesn't seem to work out of batteries, but we'll see if we manage to find some. In the meantime, I'll just remain close to the screen. So this is where we stopped last time. You might remember that Spark is about querying RDDs, and RDDs are collections of whatever, and the whatever can be key value pairs, but doesn't need key value pairs. And then we saw that we can transform these RDDs into other RDDs, and in order to do this, we use something called a transformation. And so when you create your query with Spark, with the API, you basically end up with a graph of transformation. That's a DAG, a directed acyclic graph. And nothing actually gets computed when you do that. It's at the end when you trigger an action, like printing on your screen or something, it just triggers everything. And then we saw that some of the transformations, they are called narrow dependencies. We saw that there is no spaghetti in them. It means that we can execute them in parallel over the cluster, and there is no need to shuffle things around. And when that happens, and when we have several transformations that are applied one after the other that are not spaghetti-y, that have narrow dependencies, we can optimize things by just chaining them without changing the machines. And what we end up with is this, what you see on the screen, where you see that we can split the work of transforming the RDD, the sequence of transformations, into tasks. So every task is on a partition of the input data. And we see that on every partition of the input data, we can apply the transformation function. Maybe it's filter, maybe it's map, maybe it's a flat map locally. Even several transformations locally, like maybe here I take this value in the data, I apply a filter, and then I apply a flat map, for example, and so on. So it's sequential within a task, sequential across tasks within the same slot, same CPU core, and then it's in parallel across the cores, and we spread the tasks all over. So this is very important. It's not that it's new to you, right? This whole idea of slots, tasks, partitions, and so on, we saw it in MapReduce too, right? And calling the functions. What's new here is that unlike MapReduce, we can chain multiple transformations, and if they are not spaghetti-y, then we can actually chain them locally in this way across the tasks. So you can actually control how many slots you want, how many executors you want, how much memory per executor you want, how many cores per executor. This is all within your control. And you can do this on the command line, because whenever you submit an application to Spark, you can use Spark submit. Of course, for the exercises, we use the convenience of Jupyter notebooks where you don't have to worry about these things, but you can, if you want, worry about these things. And then you have to use the Spark submit command. Then we can specify the number of executors. So the executor that would be this here, that's one executor, a second, oh, thank you. A second executor. Let's see now. That works. Oh, seems to. Wonderful. Now the clicker works. I can walk a bit in the lecture hall now. Okay. So with the magic command, the magic parameter num executors, you can select. In that case, it's 2 executors, right? But you can say, okay, I want 42 of them. You can control the number of cores per executor. You can set it to 2. Then an executor will have 2 cores. If I come back here, that's actually the case. Every executor has 2 cores, so there are in total 4 slots, 2 times 2. And then you can control how much memory you want per executor. So in that case, 5 gigabytes. Note that the executor memory is shared across the cores in the same executor. So if you have 10 gigabytes of memory for executor 1, this is shared between core 1 and core 2, right? Okay, so it gives you some flexibility, this sharing of the memory. Okay, and then you can put it together. So in that case, I have 42 executors of each 2 cores, so I have 84 cores in total. And every executor has 3 gigabytes of memory, so I have 126 gigabytes in total that is being used. I just need to multiply with the number of executors. Okay, and my application.jar is just some zip version of let's call it that way, of a Java program that you can just execute on Spark. These are the power users who do it that way. In order to do the exercises and at the exam, you actually don't need to worry about that because again, you have the comforts of the Jupyter notebook where you can just write PySpark and it just works, right? Okay, but at least you know that this exists and you know that you can control these parameters. Okay. And of course, now what I told you about these transformations that can be chained in this way, like this, it's not always the case, because you might have noticed when I showed you this huge reference menu of transformations that some transformations are actually spaghetti-y. And this is what they look like when they are spaghetti-y. And of course, then you can no longer parallelize and split in the same way as you can with the narrow dependency transformations. So examples of transformations that are spaghetti-y are when you do, for example, a join, or when you compute distinct values, that's also spaghetti-y, or when you group by key or reduce by key and so on. So basically, it's when you have these arrows all over the place. And in that case, we need to shuffle, just like in the middle of the MapReduce. So then we have to basically stop here what we are doing, shuffle around over the network, and then we can do things in parallel again, right? Yeah, so there's no choice. We have to do it. We have to shuffle around, and we say that we start a new stage. Stage is just a synonym for phase, right? In MapReduce, there's the map phase and the reduce phase. In Spark, we call them stages instead of phases. It's just the same. So basically now, if I zoom out, I'm going to have a first stage with plenty of narrow dependency, non-spaghetti transformations like filter, map, flat map, and so on. And then at some point, I have a transformation that's spaghetti, for example, group by key. Then I have to shuffle around. So the data gets shipped over the network across the cluster. And when I'm done, I start the second stage. So in that case, I was out of luck because the next transformation is again spaghetti. So I have to shuffle around again after that. That's the end of stage 2. And once it's shuffled, I go to stage 3. And in stage 3, we were lucky again that we have a narrow dependency transformation. So I was able to chain them. For whom is that clear? Right? Whenever you have spaghetti, you have to shuffle around. Whenever you do not have spaghetti, you do not need to shuffle around, and then you can optimize things a little bit. So what is a Spark job? In the end, it's just a sequence of stages, right? It's just a sequence of stages. And the stages, it's really, you can actually observe, there is an interface where you can connect to when you execute a Spark job, and you will actually see in this interface, this is the current stage. And you see in parallel the progress of the number of partitions. Then it reaches 100%, and then bam, shuffle. And then you see again stage 2. Then you see the percent progress with the number of partitions with completion bars. Then it's done and so on. So from top to bottom here, that's the elapse of time, right? You have first stage 1, then stage 2, then stage 3. And at the very end, then you have the outputting on the screen or something, right? The data that is shuffled in the middle, that's intermediate data. It's not going to go to your screen. It's not going to go anywhere. It's just intermediate data flying over the network. We also say that this data, the shuffling data, is materialized because you actually have it fly over the network. The data that would be in the middle of stage 1, so right here or right here, does not get materialized. It's computed on the fly on the computers, right? Item by item, but you never materialize the connection, the collection, the RDD. All right. So this word materialize is important. When you materialize something, it means that the RDDs actually exist somewhere. You basically have the actual data stored across the cluster. All right. Who understands materialize, the notion of materialization? Yes? Okay, very good. That's a very important word, materialization. Okay. And in general, of course, you know that not all transformations take only one RDD. You have transformations that take several RDDs. An example of that is the Cartesian product, another one join, another one intersect, union, and so on. So this might instead happen, that you have stages organized like that. but you still have this notion of the order of the stages, that you have stage 1 and then stage 2 and then stage 3 and then stage 4, right? Of course, you could also first do stage 2 and then stage 1 and then stage 3, right? But you do need to do them one by one, the stages, right? Okay, so that's what happens in general. Okay, so you see the mess that is going to be with the join. It's not just one shuffle, it's 2 shuffles. That's a huge overhead over the network. And of course, you don't want to insist too much on them and you want to keep it to the minimum, right? Okay, so that's just for you to learn the words that I put this little schema here just in order to help you in terms of what is a job, what is a stage, what is a task, and what is a transformation. So a job, that's let's call it your final goal when you trigger an action that creates a job. The job is to set up all the computations and get you the outputs that you want. That's the job. That's the overall thing. A job is made of a sequence of stages, stage 1, then stage 2, then stage 3, then stage 4. So it's the completion of the job stage by stage. And a stage can either be seen as a sequence of transformations, filtered and mapped and flat map. They are all narrow dependency and can be grouped together. So that's a vertical way of seeing it. Or you can see a stage horizontally as a set of tasks that need to be executed, right? It's just 2 ways of looking at it. It's just like you have a cake, you can either cut it horizontally or vertically. That's just 2 ways of seeing it, right? Okay, but you cannot split it both vertically and horizontally. It makes no sense in that case, right? So you just have these 2 ways of looking at a stage. So who understands what a job is, what a stage is, what a task is, and what a transformation is? Okay, very good. So note that a job can be made of multiple stages. A stage can consist of multiple tasks, and it can also be made of 1 or more transformations on the logical level. So the tasks are a physical detail. That's a physical implementation on the cluster. The transformations are a logical detail. This is what you as a user write in your Jupyter notebook, the transformation. Okay. Now, how do we make things better? I'm not going to go too much into details, but just a few tricks. Imagine that you have this DAG of transformations. This is what you want to run. There is no action yet. So right now, nothing is actually computed, but then somebody triggers an action there. So what's going to happen? Then the entire cluster will set itself into motion, and then there will be the stages with the data flowing around, shuffling, stage, shuffling, stage, and so on. And finally, you have your outputs. Then somebody else reuses that DAG and triggers an action here. What happens is that, again, the entire cluster will be put into motion with a stage and then shuffling, and then a stage and then shuffling, and so on. And then somebody else reuses again the same DAG and triggers an action here. Then you set up again the entire cluster into motion to recompute everything. Now, that's not very efficient, right? Because we just kept computing the same things in there. There's a huge part here at the top with these 1, 2, 3, 4, 5 RDDs that are just always the same. Can we do better? And the answer is yes, we can do better. What I can do is that I can pin the RDD that is right there, meaning that the first time it's computed, I put a pin on it. It's like you have this also on your computer or maybe even on your phone. It's just in order to force something to remain on your screen, right? So I can pin the RDD here. And what that means is that I materialize it and I keep it. I don't delete it. I preserve it in memory or on disk or whatever. And what happens is that then when I re-trigger the action, I do not need to compute again these first 4 RDDs that you see on the top. Now, that was already done once. And since we pinned the one that has the black lines around, then it's more efficient because then we can just trigger computation starting with this pinned RDD. For whom is that clear? Okay, so it's an optimization. This is called persisting an RDD. It can be persisted in memory, of course, across the clusters, the memory of the machines, or it can be put on the disks of the machines, but basically you persist it. Okay, that's a first improvement. Then there's a second improvement for the shuffling. How can we keep shuffling to the minimum? Can we do less shuffling? And in fact, the answer is yes. Sometimes you can actually prepare your data, distribute the data over the cluster in such a way that shuffling is not actually needed. How can it be? Well, imagine, for example, that what you want to shuffle is because of a grouping. You're grouping your key values. Let's say you have an RDD of key values and you want to group by key. Imagine that the data that you want to group on is not just randomly spread over the cluster. It has a pattern. And the pattern is such that all the key values with the same key are already on the same machines. All the yellow keys, they're on machine 1. All the red keys, they're also in machine 1. All the blue keys, they're on machine 2, and so on and so on. Who understands that in that case, you don't need to shuffle anything? Because all the keys you need in each group, they're already on the same machine. So in that case, the spaghetti goes away, and you don't need to shuffle. Now, of course, this is assuming that the data is distributed in that way. But it turns out that Spark allows you to get that kind of control. You can actually order Spark, instruct Spark to prepare the data in such a way that the keys are going to be on the same machine. If you do this, then you will have no shuffling. This can be particularly important, for example, if you have several spaghetti transformations on the same keys, then you would have a shuffling every time. But if you pre-partition, you already pre-distribute the data, having the keys on the same machines, then you have no shuffling anywhere where these keys are actually used. And Spark is smart enough to figure it out. If Spark has the knowledge that the keys you group on are already grouped on the same machine, then you don't shuffle. So this is great because in that case, for example, imagine I'm taking again the same example here, but imagine that on the right side of the join, a join also is trying to group by key, right, in order to join. So imagine that on the right side of my join, I already have pre-partitioned the data in such a way that the keys are already together in the same machines. Then I don't need to shuffle on that side, right? And I only have the left shuffling. So the left shuffling will bring the keys from the left on the same machines as done on the right, but the keys on the right, they will just stay where they are because they're already grouped on the machines. For whom is that clear? Okay, this is already advanced, right? In practice, you won't have to actually worry about this for the exam, at least the practical assignments, but just so you know that it is possible to reduce the shuffling. But of course, what is for sure is we will never, ever reduce the shuffling to 0. There is no way. Shuffling is necessary. If you cannot shuffle the data, there is no way you can actually work on the data. Because when you work on the data, you have to put the data together in order to extract value from it. So we won't get 0 shuffling in general. Of course, in some jobs, you might have 0 shuffling, but in general, we will not get 0 shuffling. But we can try to keep it to the bare minimum, as little as we can. Okay. Okay, now I'm moving on to something completely different and new. It's one of well, it's no longer that new anymore, but it was new back then. It's the idea that Spark as such, with RDDs, does not respect data independence. Do you remember what data independence is? Like, for example, with relational databases. Data independence is the idea that it's easy for the user. For example, with PostgreSQL, you as a user are sitting in front of your screen and you're just looking at tables and you're just writing SQL and the tables magically appear on your screen. You're not worrying about what's going on in the background on your computer. You don't care about this. But the problem is that with MapReduce or even with Spark RDDs, you do care. You are actually working on a physical level with transformations and having to write a lot of code in Python that is very complex and so on. That is a breach of data independence. That's not good. It's too complicated. It's too complex, right? It's too complex. So how can we bring back data independence to hide all of this from the user and make it easier? Even better than that, could we even bring back something like tables to the user, that the user just manipulates tables, or maybe something else than tables, but similar to tables, and they don't have to worry about the rest, about transformations and everything. What if, even better than that, we could even have a language like SQL that we could use instead of these transformations, actions, complexity, right? And the answer is yes, there is indeed SQL, Spark SQL. There is a Spark version of SQL that replaces all of that. Then you just sit in front of your Jupyter notebook and type SQL, and it just magically works. This is what the Spark team figured out at some point, and they added back some data independence to the system. And that probably is intuitive to you, because when we were looking in the transformations, very intuitively, when we saw, for example, this filter transformation, we commented on the fact that the filter transformation, kind of like a where clause in SQL, right? You filter out some data. The group by key is kind of like a group by, right? We also have a sort transformation. It's kind of like the order by, right? And so on and so on. We have a map transformation that could be used to do projection, right? You would project for every row to just the columns you want, right? So you already noticed that as a Lego game, this restaurant menu of the transformation kind of has all the ingredients we need for the relational algebra, and we could technically put SQL on top of that. Okay, so instead of tables, what Spark actually exposes is a more generic way to present tables. It's data frames, and we've already seen them. That's the good news. Remember the JSON validation? Who remembers the data frames? Right? It's valid JSON, basically. That's exactly those that we saw. So here's the idea. When you have an RDD, you're manipulating these collections of whatever, right? In that case, it's a function that maps. And if you look at Python, it's super complex. Who wants to write that? Well, maybe if you love programming, you love to write that, but I don't like to write that. This is too complex, way too complex. I need to worry about too many things and the lambda notation for the functions and so on. Too complex. If my data is not text, but it's JSON, oh my, that's even worse. That's even worse. Now I have to worry about actually parsing the JSON from the data set, because Spark actually doesn't know about JSON. And then I have to use Python in order to navigate the JSON, you know, with these square brackets with a quote key and so on. That's actually a Python thing. This is how you access a dictionary, which is a JSON object in Python. This is scary. I mean, I'm a database researcher. This scares me. I don't like this. I don't like this at all. Especially, I don't want the users of my database to actually have to ever write something like this. It's too complex. So in order to fix things, let's look at the special case where my RDDs are just not collections of whatever, they are collections of rows. What is a collection of rows? Well, technically, it's kind of a table. Of course, there's a few constraints for it to be a table, right? We saw the relational integrity, the atomic integrity, and so on. But technically, if my whatever in the RDD are rows, and I have a collection of rows, then I basically retrieve tables in there, right? So that's exactly what's going to happen here. I'm going to assume that every one of my whatevers in my RDD is a row. And if that's the case, then assuming they all have the same columns and atomic integrity and so on, then I get a relational table. Now, I can also relax a few things. I can allow for nestedness. So I can, for example, say, okay, I'm not assuming atomic integrity. For example, I'm only assuming relational integrity and domain integrity. If I drop the atomic integrity, I just allow for tables in tables in tables in tables. But we saw that in DataFrames, we can actually do that, right? When you have a JSON collection and you have objects in arrays, then this is basically technically the same as nested tables. Then I have DataFrames. All right. So by assuming that I have rows in my RDDs and the rows can be nested, then I get a data frame. So the way that data frames are handled, it's super efficient, and this you don't need to worry about the user, just that Spark is able to efficiently store these data frames column by column in memory. In fact, it's the same thing that Parquet is doing. You remember the Parquet binary format? When you validate JSON, you get a data frame, then you can store it as Parquet with the schema. Parquet is actually storing it in columns. So can Spark SQL. Why is that useful? Because when you query your data, maybe you only need the first 2 columns. Maybe you ignore the other columns. Well, if they are already stored like that, then you just drop them and ignore them. And that's actually very efficient because you only look at what you need. The consequence of this is that if you use Spark RDDs, that's going to consume a lot of memory. Imagine you have an RDD of JSON objects, then the keys of the objects will keep appearing in every single object, right? Remember, in a JSON data set, the keys are repeated every time. So if you have an RDD of JSON objects, it takes a lot of memory. But if you store things in data frames, it takes less memory because, for example, the name of the column is only stored once in the schema. And then in the actual data, you only have the values that you have in your data frame. So data frames are actually less consuming in memory, just like they are less consuming on disk if you store data in Parquet rather than as text JSON. Okay, and now comes the magic. If you ignore what's around it, this is Spark SQL. The only reason for the rest is that Jupyter Notebooks needs Python, right? But we see that for the exam, you won't even have the Python thing. There's directly a Spark SQL cell that you can write. But anyway, do you see this? Select star from dataset, assuming dataset is some RDD, that is a data frame. Select star from dataset, where guess equals target, probably going to be implemented as a filter transformation, but why do I care? I'm just writing SQL. So where guess equals target, order by target ascending, country descending, date descending. Who understands that SQL? Right, we've covered it in the brush up. It's almost the same SQL. Now it's kind of the same SQL because, as I told you, there's plenty of dialects of SQL, right? There's Postgres, IBM has a close one, but different one, Microsoft yet another one, and Spark has yet another one. But in essence, it is going to be SQL, right? They all look alike. So now everything that you worked on during the brush up at the beginning of the semester now will be directly useful to you again, because that's almost the same language. So on the exam, you're going to have Postgres SQL, you're going to have Spark SQL, but it's very close. They're very close to each other. And in the exam, and also in the exercises, you won't need to type this df, blah, 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 that is around it. You won't need that. You just have this Spark SQL magic, where you directly type the SQL, just like for PostgreSQL, and it will just work on the data frames. You would see it's a delight to actually use this. And what happens is that now, when we actually try to read data sets into RDDs from CSV, for example, then instead of creating an RDD, it's going to create a data frame like this, right? So it's very natural. The first column in that case is an integer. The second one is a Boolean. And now we work on a data frame and we can use Spark SQL. Now it's JSON. Imagine that I have JSON now. So I didn't validate it, but you kind of want to validate it. Who feels like they would like to validate this JSON? It's very highly structured, right? Foo is always an integer and bar is always a Boolean. So you would have a schema, right, that says foo integer, bar Boolean. You don't even need to do it yourself because Spark is going to automatically detect the schema. If you feed that into Spark data frames, Spark will automatically figure out that's an integer and that's a Boolean, and it will feed it in the table in that way. Right? If you have arrays of objects, the same. It's going to figure it out with a data frame with nested tables automatically. Okay. There are people out there that still love to write these kind of things. They can. So if you don't like Spark SQL and you really want to write something like transformations, there is a way of working on data frames with transformations in a very similar way to RDDs. Just don't be surprised, because even though it looks the same, it might not be exactly the same names, exactly not the same transformations and so on, but this exists for those who like it. In my experience though, most of you or most of your predecessors preferred Spark SQL. Right? Let's do a little poll. Who would prefer to write just Spark SQL, just the part in blue, not the rest? On my side, who strongly prefers to write this? We also have some of you, right? Well, you can do both. You can do what you prefer. Even on exam day, if you don't like Spark SQL, you are totally free to write things that way. It works too. Okay? All right. Now, Spark data frame is yet another implementation of data frames. And of course, there is a type system. But I have super good news for you. is that the type system corresponds exactly to what we've covered in the data models lecture a few weeks ago, right? Look at this. We have numbers, byte, short, integer, long, float, double, decimal. We've seen that already. We have strings, we have Booleans, we have binary timestamps. We've seen all of that. We know all of that. Structured, we have arrays. We've seen that. Struct, it's just objects. Map, it's just a different way of objects. But basically, this is all familiar territory. In fact, it's so familiar that I bring you this table right here, this correspondence table between, so JSONic, that would be the same as JSON, XML schema. So these are the types that we've already seen. In the middle, you have Python, right? This is what it would correspond to in Python 3 more exactly. In the second one, you have Java. If some of you actually like Java, then this would be the Java equivalent. And on the left, the first column, this is the data frame menu. You see, it's beautiful. There is just a correspondence there. So the good news is you don't have to really learn much about that, except that it's just different names, right? But it's just blah, blah, blah type, blah, 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 blah type, right? So, okay. Who finds it easy? I mean, this is a déjà vu, right? There's nothing really new in there. Who finds it easy? Okay. It's just that the data models lecture that we've spent 1 or 2 weeks on, these are now the benefits we get out of that. And all of these types, these are the types you can have in your data frame columns, right? Also, I could even have put the PostgreSQL types in there as well, right? If I wanted to, I could add a 5th column with the PostgreSQL types. Okay. So these are the atomic types. These are the complex types. And here you see that struct is basically an object. Array is an array. And then in Java, that would be lists, maps, and rows, and so on. But the correspondence is there. Map type, map is used a bit less. So the ones you really see a lot is array and structs, which corresponds to JSON arrays and JSON objects. Map is kind of like a JSON object, but all the values have the same type, right? Which in general is not the case. In a JSON object, foo could be an integer, bar could be a date, and so on. But in a map, all of the values are the same. For example, you could have a map from country code to country name. That would be a map, right? So it's a specific kind of struct, right? There's also more to it, but I don't want to annoy you. But you don't need to worry too much about maps. It's array and structs that are important, and they correspond to arrays and objects in JSON. Okay. I already put JSONic because we're going to study the language in a few weeks, but it's the same ecosystem as JSON, XML schema, JSON, and so on. Okay. Now, if you want to read from a data set, you can use these functions like Spark read JSON, Spark read Parquet, or you can read Parquet also directly to a data frame, CSV, text. JDBC is if you connect to PostgreSQL. You can even connect to PostgreSQL and look at your table as a data frame, and so on. On exam day, you don't need to worry because this you'll get for free. There will be a data set on the computer, and the line to read the data set will already be in the Jupyter notebook, so that you won't need to worry about on exam day. But just to show you all the schemas you can actually open to data frames. This slide is less important. It's just a curiosity. Is that you can also define the schemas of your data frames in Java or in Scala and so on. So you can actually say my data frame first is a string, last is a string. It's like a JSON schema or a JSON schema. But actually, you can define the schema with a Java class, right? So it's an advanced feature that you don't need too much to worry about, but I'm just telling you that this actually exists, right? If you know the schema of the data frame, you can do that. Okay, but we won't have that in the exam, just generic data frames. Okay. So a few words on Spark SQL. It's really just similar to the SQL that we know. So you have the choice between this or this. And what's going to happen when I have slides. Yes, I have slides on Spark SQL, but I just wanted to say this before we get to Spark SQL. So what happens when you write Spark SQL or when you write the transformations like that, it doesn't matter. Spark will automatically convert the data frames to RDDs in an optimized way, and it will automatically convert Spark SQL to RDD transformations automatically. If you wrote this, it will automatically convert the data frame transformations, these are data frame transformations, to RDD transformations, right? So we say that these data frame transformations, they're a logical plan. So with Spark SQL, and it converted to a physical plan with the actual RDD transformations. But you see the big leap, the breakthrough that we have done. With this, you don't need to worry anymore about RDD transformations or filter or map or flat map and so on and so on. And in fact, hopefully you realize with the exercises that you will start preferring writing these kind of things, most of you, than the low-level RDD transformations, especially if you're manipulating JSON. You'll quickly see that manipulating JSON using RDD transformation is very annoying. It's very complex. All right. But we still use all of them in the exercises. We train you on RDD transformations, on Spark SQL, on JSONic, and so on, just so you see the difference. You see that you can do the same things, but with different tools, and then you see for yourself the tools that you prefer and those that are the most convenient. This here is a picture of everything that happens magically for free in the background without you needing to worry about it. This is just the pipeline of optimizations that is automatically set into motion the minute you press enter after typing your Spark SQL query. It just optimizes things like crazy and figures out ways that it can run your query faster. And this is called Catalyst, the technology behind this. All right. So now all you need to worry about is you take a CSV data set, a structured JSON data set that could be validated, or a Parquet file or whatever. And all you need to do now is type SQL, just like we saw for PostgreSQL. So you see select from where, group by, having, order by, limit, offset, it's all there. Yes, even offset, that's as of Spark 3.4, offset actually was introduced. So it's very, very new, just a few months old. They didn't have offset before, but now they do. Right. Who understands that slide? Just good old SQL, the one we know. Okay, so you don't have too much to worry about, but you can probably guess when the shuffle is going to happen behind the scenes without you actually noticing. It's the group by and the order by will trigger the shuffling, right? When you have the where, that's going to be a filter transformation, so it's a narrow dependency. Having is again a filters after the grouping, so it's a narrow dependency, and so on and so on. So in that case, we're going to have two shuffles with group by and order by. And in fact, there's going to be only one shuffle. Can anybody tell me why in that case there's going to be only one shuffle? The second one will not be necessary. You see that what we are grouping on and ordering by is the same country. This is the reason. So Spark is automatically going to sort, group and sort at the same time in a single shuffle by country, and that's it. It only needs to do it with a single shuffle. You as a user don't care. You just type this and it will just work, right? That's the magic of having a high-level language. Okay. Any questions so far? Yes, maybe we can throw the microphone. Oh, almost. We're going to do it in 2 hops. Thanks.
I wanted to ask, is it Catalyst or is it SQL that does that handles the 2 shuffles so that it's just one shuffle?
Catalyst. SQL is only a language. That's a language. SQL can be used with PostgreSQL, with IBM, with Microsoft SQL, with Spark SQL, and so on and so on. It's only a language. And Catalyst is the underlying engine that figures out how to best execute SQL in the case of Spark SQL, right? PostgreSQL doesn't use Catalyst. They probably have their own optimization engine, right? Thanks. Oh, wow. Okay, so this is the good old SQL that we know. It's going to take care of things automatically. Okay, however, and this is almost done now with actually this lecture, but I just want to make you aware of something. When we looked into PostgreSQL, we only dealt with relational tables. Everything was flat. There is no nested table. We only have atomic types in the columns. But with DataFrames, we saw that it's different because we now don't force the atomicity. We allow for nested tables in DataFrames, right? We could have a column that itself has lists of objects, right? So these are the ones we saw in the data modeling lecture. So this is challenging. If we want to actually use a language like SQL in order to handle this nestedness, then we need to kind of adapt SQL to it, because SQL was never made for that. When it was designed, it was just made for flat tables, not for nested structures. So this is why, since Spark wants to support data frames, they had to extend SQL a little bit in order to be able to also deal with nested tables. So these are Spark-specific extensions. You will not find them in other products, or maybe they will be different in other products. And the reason I'm showing you that is that I want to scare you actually with this. I want you to see that this is complex, because we'll have much easier ways a bit later. But just so you know that you can actually do this. If you look here on the top table on the left, this is a data frame. How do you see that it's not a flat table? Because the third column is actually structured. The third column, these are arrays of strings, right? So we are nesting things in there. It's not a flat table. Well, there is this explode function that you can add to SQL, select last explode countries. What it's going to do is that it's going to take each one of the values in the array of strings, D, I, C, H, A, and so on, and it's going to put them in separate rows. What about the other columns? Well, it's duplicating them. So for example, you have Albert Einstein that has D, I, C, H, A, B, E, U, S. Well, he was in so many places. We are just copying and cloning Einstein, 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 so 6 times, and then we put each string in there. Ramanujan, there's 2, Kurt Gödel, there are 3, and Mirzakhani, there are 2, right? Who understands this? Okay. So in that case, it looks relatively simple, because you just call explode and it's just going to work. But the difficulty here from a language design perspective is that explode is not really a function. It's not returning anything, right? Explode is just causing the table to be transformed in that way. So from a language design perspective, it itches a little bit, but it does the job. Now, this is the simple case. In more complex cases, you actually would use lateral views to do the same thing. So you say select last and country, lateral view explode countries. It's as if it was creating a table on the side with the exploded content and then joining it back, right? So this is what it does. And then, as you can see, now we have objects in arrays. The SQL query becomes very complicated to understand. This is what I want you to see here, right? You can try to understand it and make it work, and probably you have it in the exercises. But what I want you to see here is that SQL was never made for nested data. It was never made for that. So anything that you try to add to SQL is going to basically look a bit artificial, right? And we'll see in a few weeks that we can have languages that are specifically designed for nested data that will be simpler to write than lateral views, right? But for simple cases, it works. I mean, if you just have a single explode like that, then Spark SQL is totally fine, right? It's for when it becomes more complex that it can quickly become a nightmare to actually write queries, okay? But I'll come back on that. So this is for nested arrays that you can use explode, and then you also have nested objects. And for nested objects, you add a dot to the language, just like you have in Python or in Java. So if you have you can notice here we have a data frame, and the first column is an object. So we can say name dot first, and then get Albert, Srinivasa, Kurt, John, Alan, Mariam, and then name dot last, and then we get Einstein, Ramanujan, Gödel, Nash, Turing, Mirzakhani. All right. This is the dot for the object. So explode for arrays, dot for objects. Okay. And here is when it breaks, because of course you can push it, but at some point it's going to break. And this is where it breaks. It breaks when the data you're looking at, JSON data set, is actually not valid or cannot be validated so easily. Look at this. What do we have here? Foo is most of the time an integer, but on the third object, it's not an integer, it's an array of integer. Now, for a JSON data set, that's totally fine. We always allowed that, right? You can put whatever you want in a JSON collection. It's just that in that case, writing a schema to validate that would not be that easy anymore, because you cannot just say foo has a certain type. It has several types. It's sometimes an integer and sometimes an array. So what if you rely on Spark? Because I told you that Spark figures it out. Does Spark really figure it out? Well, what's going to happen when Spark sees that? It's going to say, okay, foo looks like an integer. Okay, 1, 2, still an integer. Oh, 3, 4, that's an array of integers. Now I have a problem. What Spark does is it puts it in a string. It puts it back in a textual format. So the character 1, the character 2, the character square bracket 3, 4 square bracket, and it basically puts it back as a JSON string, a serialized JSON string. And essentially, what Spark is doing is just making it your problem. Okay. You gave me a data set where not all the keys have the same types. Your problem, you'll deal with that. So it just gives you that data frame here. Foo is a string, contains serialized JSON, and you as a user, the burden is on you to now do something with this, right? These are the limits of DataFrames. These are the limits of Spark SQL. This is where it breaks. And now, when you have something like that, that's no longer the right technology to use, right? It's the right technology. Yeah. Yes, it's the break. Yeah. That's the last slide, actually. Oh, no. Yeah, that's the last slide. Let me show you. Then we take a break. I'll give you 2 more minutes. This is just an illustration that you can convert back and forth between DataFrames and RDDs. But again, this is advanced, and you don't need to do it at the exam. Okay, well, you deserve the break, right? Right. So this is the end of the Spark lecture, and I just wanted to show you the limits right there. That this is when it stops working as intended. So we are stopping here. I think it's 9:03, so we are going to be back at 9:18 for the continuation, and you get your full break with 15 minutes. And then I'll start with document stores and MongoDB in the second hour. So thank you very much, and see you in a quarter of an hour.